Rational functions and graphs. Now we've heard about rational numbers before. Rational numbers are just a fraction involving two different integers where the denominator is not equal to 0. So some examples of rational numbers are -2/3 or 9, which can be written as 9 over 1. Now we can have rational functions as well, where we have p of x over q of x, where p of x and q of x are polynomials. So instead of just numbers, we can have polynomials. Now those polynomials can be of any degree. They can even be a constant. So some examples of rational functions include f of x is equal to x over x plus 1, where we have linear term over linear term. G of x, where which equals to 10 over x minus 4. So we have a constant over a linear term. H of x, we have a linear over a polynomial. J of x, we have a linear over a quadratic, and any other combination. So we can even have the same degree on both the numerator and the denominator. Now when we're looking at rational functions, we're going to look like what their graphs look like. We're going to explore that. We know how to graph polynomials. Let's look at how we can graph rational functions. So let's start with f of x is equal to x over x minus 1. Now the first thing you want to notice about rational functions is that we have a denominator. And in that denominator right here cannot be 0. So we need to look at the values that would make that 0. So if we look at x here, if I set x minus 1 equal to 0, I will find that x is equal to 1. So when x equals 1, that denominator is equal to 0. And that can't happen. And that gives us our first asymptote. That's where the graph approaches that asymptote but never crosses. So f of x is going to approach that vertical asymptote, but it's never going to cross it. So at x equals 1, that's a place where that graph will never be. And so I can go ahead and notate that as a line. So all along here is where x is equal to 1. That is my vertical asymptote because it creates a vertical line. Now looking at horizontal asymptote, we want to look at long-term behavior. What happens as x gets to be a really, really big positive number or a really, really negative number? Now we want to look kind of at the end behavior to see where the graph is going to approach. And when we do that, this -1 is actually not going to matter. So if we think about even just 100, we have 100 over 99. That's really, really close to 1. So our horizontal asymptote is really what happens as this gets to be very, very positive or very, very negative. And it starts to look like x over x or 1. So our horizontal asymptote is y equals 1 for this graph. Now, if we wanted to find our y-intercept, we would go ahead and set x equal to 0. So if we want to find the y-intercept, we put 0 in for x. So I have a 0 over 0 minus 1, 0 over -1, which is going to give me a 0. So when x is equal to 0, f of x is also equal to 0. Now when we're looking at the x-intercept, we want to set f of x equal to 0. And so to make this f of x 0, if the numerator is 0, then the whole thing is 0. So we really only have to look at what makes that numerator 0. Well, in this case, we know that the x-intercept and the y-intercept is the same, but if we were going to go through the procedure, we'd set x equal to 0 and figure out what x is. Well, it's obviously 0. So both our x and y-intercept are 0 here. Now when we have that, we have our horizontal asymptote and we have our vertical asymptote. Our horizontal is y is equal to 1, and we got that by looking at what happened when x became very positive or very negative. Now we want to look at what's happening on both sides of that vertical line. Now the graph can't do something like this because otherwise it wouldn't be a function. It would hit, that vertical line would hit the graph twice. So we know it's either this quadrant I'm going to see the graph or this one. And the same is true on the other side, either this one or this one, but not both, otherwise it wouldn't be a function. So we're going to choose some values, and you can see I've already chosen a few, my green dots here, but I'm going to choose a couple values on this side and this side. Now I already have this one right here. Let's go ahead and choose one over here to the right. So I'm going to choose the value of 2, so that's right here. And I'm going to plug that into my equation to see what f of x is. So I have 2 over 2 minus 1. 2 minus 1 is just 1. So 2 over 1 is going to give me a 2. And I can go ahead and plot that point. Now I'm going to test another value. I'm going to test a -2. Now I know it's starting here. It's probably not going to cross this line right here, and I know it won't cross my vertical asymptote. And so I expect it to be approaching this horizontal asymptote right here. So I substitute a -2 in. I have a -2 minus 1. That gives me a -3. So I have a -2 over -3, which is positive 2/3. So that's exactly how I thought my graph was going to go. And I want to try another value. I'm going to try 4 here. So that's 1, 2, 3, 4. What's the graph doing at 4? So I go ahead and substitute a 4 in. I have 4 over 4 minus 1. So 4 minus 1 is 3, and that's 4/3. So when x is equal to 4, y equals 4/3. And then I can go ahead and use those points as a guide to draw the graph. I know it's going to be approaching the asymptote here and approaching the asymptote here. Getting closer and closer. And same is true up here. It's going to be approaching, and it's going to be approaching. Okay, so once I have a couple of points, I can figure out what the graph's going to be doing. If you need to try more points, feel free to try more points to get a better idea. So let's look at another example. Let's look at g of x is equal to this constant over this linear term. So I want to first look at that denominator to find my vertical asymptotes. What would make that 0? Well, when x is equal to 4, that denominator would be 0. And so I know anywhere x is equal to 4, my graph is not going to be allowed to be there. And so that's where I get my vertical line, x equals 4. And I can go ahead and draw that as a dotted line because I know that this graph is not going to cross that. Now, in looking at my horizontal asymptote, I want to look at what happens when x gets to be a very large positive number or a very large negative number. So when that happens, I have this 10 over something that's either really, really big or really, really negative. So 10 over a million or 10 over negative a million. That's going to be awfully close to 0 if I have a constant over a really positive or a really large negative number, a really negative number. That's going to be close to 0. So my horizontal asymptote is going to be at y is equal to 0. Now we're going to go ahead and find the y-intercept as a point on my graph. So to do that, I set x equal to 0. I plug in a 0 for x. So I have 10 over 0 minus 4 is equal to -10 over 4. I just moved that negative up to the top there. And then simplifying, I have -5/2. So my y-intercept is at 0, -5/2. And I go ahead and plot that point. Now, if I were to guess how this graph would go, I could see it approaching right here, and then down here, and then I don't know what's happening over here. So I'm going to have to try some more points. Well, let's first see if we can find an x-intercept. So to find an x-intercept, I want to set this numerator, this 10, equal to 0. Well, 10 is equal to 0 never, ever, so there's no x-intercept, which makes sense because I have a horizontal asymptote at y equals 0. So then I'm going to try a few points this way and a few points this way. So I'm first going to try 6. Now I chose 6 because it actually makes my denominator nice when I pair it with my numerator. But you might have to try a few values before you see that. But I have 6 minus 4. 6 minus 4 is 2. 10 over 2 is going to give me a 5. So at 6, at x equals 6, my graph is at 5. So I go over here to 6 and I come up here to 5. So I'm thinking my graph is going to do something like this. It's going to approach both those asymptotes. Now I want to try what's happening on this side to see how quickly it's approaching this asymptote. So I'm going to try a 3. X is equal to 3. I have 3 minus 4. That gives me a -1. 10 over -1 gives me -10. So that's way down here, which I expect because it's approaching that vertical asymptote. Now let's try a couple other values. Let's try a -1. So if if I put in a -1 here for x, and I have -1 minus 4, that gives me -5. 10 over -5 gives me a -2, which is what I expected. It's slowly approaching that. Let's just try one more. I plug in a 2 right here. 2 minus 4 is going to give me a negative 2. And so I have 10 over negative 2, which is going to give me a negative 5. So I kind of have an idea, and if you need to, plot more points to kind of see what the behavior of this graph is going to be. So I know it's going to curve up and approach here, and then it's going to slowly curve down and approach this asymptote. It's not quite as quick as the other one. It's not approaching it quite as quickly. And then I have this approaching this. So still a function because it passes that vertical line test. And you can always plot more points to get a better idea. So let's look at one that has a quadratic in the denominator. So I have a constant on top and a quadratic on the bottom. Now looking at that quadratic, I want to find out where the denominator is equal to 0. And so what I need to do is probably factor that to set it equal to 0. And if I couldn't factor it, I could use the quadratic formula or I could complete the square. But this one's easy, I can factor it. So x plus 3, x minus 2. Now I can set that denominator equal to 0. I can set each of these equal to 0 because of the zero product property. And then I get x is equal to negative 3 and x is equal to 2. Now I can't have those values in the denominator, so my vertical asymptotes, I have 2 this time. I have x is equal to negative 3 and x is equal to 2. And I can go ahead and plot those on my graph as my vertical lines that the graph is actually not going to cross. Now looking at my horizontal asymptote, I'm going to look as x becomes very positive or very negative. And really I only need to look at that x squared because that's going to take over all of these other terms. So if x gets really, really big, I'm going to have a huge number down here. And 6 over a really big number, or 6 over a really, if I have a negative value right here, it's actually going to be positive. But it's 6 over something really, really big is just going to be close to 0. It's going to be approaching 0. So my horizontal asymptote is going to be y is equal to 0. So I went ahead and plotted that. It's kind of hard to do that when it's the same as your x-axis. So I sort of dotted it and drew my dotted lines a little bit further out. So I'm going to check for my y-intercept, and to do that I set x equal to 0. Now I can use either this one or this one. It doesn't really matter. They're just different forms of j of x. They're exactly the same. I'm going to choose this one. It's a little bit easier. 0 squared plus 0, that's just 0, minus 6. So this whole denominator is negative 6. I have 6 over negative 6, which gives me a negative 1. So my y-intercept is at 0, negative 1, and I went ahead and plotted that. Now I don't really know what this graph is going to do yet. I don't have enough values. I could have it be up here approaching those asymptotes or down here. I don't know what this middle thing does. It could even go down like this, or maybe like this, or maybe like this. So I'm going to have to plot some values on either side of my y-intercept. And also the same is true over here. So let's look at the x-intercepts, see if there's any x-intercepts. I take my numerator, because I know if my numerator is equal to 0, the whole thing is 0. And I set it equal to 0. 6 is never equal to 0. So again, I have no x-intercept, which makes sense because my horizontal asymptote is y equals 0. So now let's test some points. I plug in a 1. If I substitute a 1 in here, I have 1 squared plus 1, which is 2. 2 minus 6 is going to give me a negative 4. 6 over negative 4 reduced gives me a negative 3/2. So when x is equal to 1, I have a negative value right here. So I'm pretty sure my graph is going to be approaching. Let's see if I can draw this. Well, it's going to be approaching this asymptote. Okay, not bad. It's going to be approaching like this. I don't know what this other side does yet. I can go ahead and test that out. I'm going to try a negative 2 because that's in between these asymptotes. So that negative 2, plug that in. Negative 2 squared is 4 plus a negative 2, which is going to be a 2. Negative 4 plus a 2. No, that's not negative 4. So if I plug in a negative 2, that's 4, plus a negative 2 is going to give me a 2, minus 6 is going to give me a negative 4. 6 over a negative 4 is going to reduce again to give me negative 3/2. So I know it's coming back down over here. It's not going to be going back up there. So I know it's doing something like this, not touching. All right, so then I want to try some values on this side and on this side. So I'm going to choose a 3, and if I choose a 3, 3 squared is 9, plus 3 is 12. 12 minus 6 is 6. 6 over 6 gives me a 1. So I know this looks like this, and so this is approaching this line and over here. Now I want to look at the other side. I'm going to choose a negative 4. That's over here on this side to kind of see what the graph does, if it's like this or if it's down here like this. Choose a negative 4. Negative 4 squared is positive 16. Negative 4 times negative 4. Plus a negative 4, which is going to give me 12. 12 minus 6 is 6. And again, I have 6 over 6 or a 1. So just like this. And then it looks something like the other side, approaching that asymptote, curving down, and approaching that one. Okay, so that's probably the trickiest one you'll have, where you have the two asymptotes and you have to figure out what's happening. In all, it's really 4 sections. This section, this section, this section, and this section. Okay, let's take a look at another one. And so we have a quadratic over a linear term. The thing is with this quadratic, if we can factor it, we can see that this has matching factors right here. So if we factor this top one, we can see we have an x over 3, or x plus 3 over x plus 3 right here, and just the x plus 2 left. So we can actually make a 1 out of that, right? X plus 3 over x plus 3. But we have to remember that my original equation does not allow for x to be negative 3. So if we make a 1 out of this, x plus 3 over x plus 3 is 1, we just have an x minus 2 left. But we know x cannot be equal to negative 3 because this is my original rational equation. And I know that x cannot be equal to negative 3. So I can reduce it to c of x equaling x minus 2, but x can't be negative 3. This is just a line right here. So x minus 2, the line has a slope of 1, and the y-intercept is at negative 2. Looks just like this. However, x cannot be negative 3. So when you are graphing your different values there, and x got really, really close to a number but didn't touch it, you made a little open circle instead of a closed circle. So that's exactly what we're going to do in this case. We're going to look over here, and we know that x cannot be negative 3. So I go over to negative 3, I come down, and I just make an open circle. That means it gets very close to 3, but it's never 3. So when you have something like this, where you have factors that cancel, you can graph the result, but you have to remember to take into account that denominator not being equal to 0 and draw the hole. All right, we're just going to do a quick review just so that you can calculate your vertical and horizontal asymptotes. I think you're probably pretty good with plugging in values, but I wanted to give you several examples. So if we had this one right here, our vertical asymptotes are going to be whenever this denominator is equal to 0. In this case, x equals negative 4. And our horizontal asymptotes we're going to look at when x gets to be a really, really big number. So when x is a big number, and we can even just, or a really, really negative number. So here, if x is a really big number, let's say x is 100, and that's not even a really big number, we have 2 times x minus 1. The minus 1 and the plus 4 are really not going to count once x gets really, really positive or really, really negative. So this is going to look a lot like 2x over x, or just 2, because the x over x will be a 1. So my horizontal asymptote in this case is y equals 2. This one is similar. So our vertical asymptote is going to be whatever makes this denominator 0. So set 2x minus 1 equal to 0, and if you do that, you'll find that x is equal to, and then solve for x is equal to 1/2. That's what would make this 0. And then looking at the horizontal asymptote, you want to think about when x gets very, very positive or negative, and when that happens, these terms really don't matter, and we're just looking at the x over x, the 5x over the 2x. The x's would cancel, and you would have, and make a 1, and you would have 5 over 2. So y equals 5/2. G of x, 5 equals 5 over x minus 2. My vertical asymptote, when the denominator is 0, is x equals 2. Horizontal asymptote, as x gets very positive or very negative, that denominator gets really, really big, 5 over a really, really big number or a really, really big negative number, a large negative number, then I know that that's going to be close to 0. So my horizontal asymptote for this is 0. And here's one like our last example where you can factor this numerator and it matches a factor of the denominator. This is a difference of squares, x plus 2, x minus 2. So we have matching factors right here. And that gives us a 1, but we have to remember x can't be equal to 2. So even though it looks a lot like a line, the line x plus 2, it has a hole in it at x equals 2. So because x cannot be equal to 2 by the original equation. Now functions, oh gosh, what is wrong with my mouth?